Now that you know how to model Boolean circuits in many different ways, including in a truth table, an equation, a VHDL model, a circuit diagram, etc., now we want to look at how do we create as small a circuit as possible. We talked already about using SOP versus POS forms to reduce the circuit. Maybe one form would have fewer components than the other, but we can also use Boolean reduction techniques to further reduce the variables and gates required within a circuit. So to figure out how to do that, I'm going to start with just a simple example, again with a truth table. So I'm just going to here draw a truth table with three inputs A, B, and C, and output F. I'll list all my possible inputs. With a 3 input, I have 8 possible input combinations. Sorry about that. From 0 to 7. 3, 4, 5, 6, and 7. And here in this example, I'm just going to say that the first two input combinations give me a 1 output. So as we learned before, for this circuit in SOP form, we could say F is equal to A naught, B naught, C naught, or A naught, B naught, C. Alright, so let's actually examine these first two rows here. If you look at these first two rows, you notice that A and B are both 0 in both cases where F is a 1, and it doesn't matter what C is. So instead of writing out A naught, B naught, C naught, or A naught, B naught, C, we don't care what C is. So this could actually be reduced to F equals A naught, B naught. And here you can actually visually see that in the truth table itself. But how are other ways to actually go about doing that reduction? Well, 10 years ago you would have had to do some Boolean algebra. So an example of that here, I'll just write it out, is you'd notice that A naught, B naught are similar in the two terms, so you factor those out and you're left with C naught or C. C naught or C is just equal to 1, 1 and anything else is just itself, so then you also end up with A naught, B naught. But instead of going through all this Boolean algebra to do this reduction, a guy named Carnot came up with a very easy to use graphical method of doing reductions called KMaps, or Carnot Maps. So here, if you look at the textbook, here's a picture of a Carnot map, and I'll explain this in a moment. So one thing about the Carnot map is to notice this numbering. The numberings inside the Carnot map represent the 0 through 7 possible choices for your input combinations. Now, why are they in this funny ordering from 0, 1, 2, 3, 4, 5, 6, 7? Well, the ordering of a Carnot map is based on what's known as a unit distant code. And what is a unit distant code? It means that adjacent cells, or numbers if you're just talking about the code, have only 1 bit difference. Okay, so what does this mean? Well, if you look at the numbers 0 and 1, you have 0, 0, 0 and 0, 0, 1. Look at these two combinations. The only difference between this number and this number is in this last bit. How about 2 and 3? Here's 2 and here's 3. The only difference in this bit combination is this last bit. So these have a unit distance because they only differ by 1 bit. Alright, let's move on to the next page to show you how this works in a Carnot map. So in a Carnot map, for a 3-variable Carnot map, we're going to have 8 cells, and they're going to be numbered 0, 1, 2, 3, 4, 5, 6, 7. And so now 3 and 7 have a unit distance, 3 and 2 have a unit distance, 3 and 1 have a unit distance, etc. So that's telling you that every adjacent cell has a unit distance to the other. Now the reason for this is because we're going to end up circling stuff in K-maps. And when we circle the stuff, what we're doing is we're grouping things that have similarities, which allow us to do the reduction. Now it's also important to know that these numbers are representing your input combinations. So I like to remember the order. So if we go look here, we have A, B, and C. A is our first variable, C is our last variable. So this whole first row is going to represent A naught. So this whole row are terms that have an A naught. Then B naught is going to be these 4 cells, these 2 columns, and C naught is going to be this column and this column. Now everything that I didn't label is the opposite of that. So these 2 here are going to be B, this one's going to be A, and these 2 are going to be C. Now you'll see how this works in a minute. So for our example, we have 1s for the 0 and 1 term, and 0s everywhere else. So we've got 1s in the K-map for these terms and 0s everywhere else. And so what you do now in a K-map is for a reduced SOP, and later you'll see we're going to do a reduced POS, but for reduced SOP form, you're going to circle the 1s. Now in the textbook it provides you all these rules for how you go about circling. So let me bring that up. Figure 9.8. Groupings must contain either 1, 2, 4, 8, or 16 cells. Groupings must have 4 corners. Groupings must be as large as possible, and use as few groupings as possible to cover the cells of interest. So as we do more examples, you'll understand what this means. So all groupings can only be powers of 2. And here this one's pretty easy because we can easily see a grouping. We put these 2 1s together. Now with that we've covered all the 1s in the circuit, and we can write our equation by looking at what rows and what columns this group is in. So this is in the A naught row, and it's in the B naught column. So there we derived the same answer A naught B naught as we did with the visual inspection and with the Boolean algebra, now just using this visual graphical tool called a K-map.